Now that we have much of mathematics under our belt, we're now in a position to introduce what it means for a model to learn. The learning part of machine learning boils down to estimating parameters based on training data. In this section, we're going to talk about the case of a predictor that's a function. We described the idea of empirical risk minimization, which was originally popularized by the idea of the support vector machine. However, these principles are widely applicable, and they allow us to ask the questions of what is learning without explicitly constructing probabilistic models. There are four main design choices, which we'll cover in this video. What is the set of functions we allow the predictor to take? How do we measure how well the predictor performs on the training data? How do we construct predictors from only training data that perform well on unseen test data? And what is the procedure for searching over the space of models? Let's assume that we're given n examples, x sub n, in d-dimensional real space that correspond to scalar labels yn in the set of real numbers. Therefore, a supervised learning setting where each xn corresponds to a target yn. Given this data, we would like to estimate a predictor f going from d-dimensional real space to the set of real numbers parameterized by theta. We hope to be able to find a good parameter theta star such that we fit the data well. That is, f of xn and theta star is roughly equal to yn. Here we use the notation y hat to represent the output of the predictor. Let's consider the example of ordinary least squares regression to illustrate the empirical risk minimization. When the label yn is real valued, a popular choice of function class for predictors is a set of linear functions. We choose a more compact notation for a linear function by concatenating an additional unit feature x sub 0, which is equal to 1, to our vector xn. That is, xn is the vector 1, xn1, xn2, all the way to xnd. The parameter vector correspondingly is then theta 0, theta 1, theta 2, and so on, allowing us to write the predictor as a linear function f of xn and theta equals theta transpose xn. That the predictor takes the vector of features representing a single example xn as an input and a real valued output f in rd plus 1, f goes from rd plus 1 to r. Given the class of functions, we want to search for a good predictor. Next, we move on to the second ingredient of empirical risk minimization. How can we measure how well the predictor fits the training data? Let's suppose yn is the label for a particular example, and yn hat is the prediction based on input xn. To define what it means to fit the data well, we need to specify a loss function, L of yn and yn hat, that takes the ground truth label and the prediction as inputs and produces a non-negative number, referred to as loss, representing how much error we've made in this particular prediction. Our goal for finding a good parameter vector theta star is to minimize the average loss on a set of n training examples. The assumption that's commonly made in machine learning is that the set of examples is independent and identically distributed. The word independent means that any two data points do not statistically depend on each other, meaning that the empirical mean is a good estimate of the population mean. This implies that we can use the empirical mean of the training set loss on the training data. For a given training set, we introduce the notation the notion of the example matrix capital X and the label vector Y. Using this notation, the average loss is given by REMP, dependent on F, X, and Y, and is equal to 1 over n times the sum of the loss. This equation is called the empirical risk. It depends on 3 arguments: the predictor F, the data X, and Y. In general, this strategy for learning is called empirical risk minimization. Continuing the last example of least squares regression, we specify that we measure the cost of making an error during training using the squared loss. So L of y and y hat is equal to y minus y hat squared. We want to minimize the empirical risk, which is the average of the losses over the data. We take our loss, L of y and y hat, and substitute out y hat. So we get the minimum of the 1 over n times the sum of yn minus f of xn theta squared. By our choice of a linear predictor, we obtain the optimization problem of minimizing 1 over n times the sum of yn minus theta transpose xn squared. This equation can be equivalently expressed in matrix form as the minimum of 1 over n, the norm of y minus x theta squared, known as the least squares problem. Now, there exists a closed form analytic solution for this by solving the normal equations, which we'll see when we discuss linear regression in more detail. We're not interested in a predictor that performs well on training data, however. Instead, we seek a predictor that performs well on unseen test data. More formally, we're interested in finding a predictor F with fixed parameters that minimizes the expected risk, R true, which is equal to the expected loss based on y and f of x, where y is the label, and f of x is the prediction based on the example x. The notation R true of f indicates that this is the true risk if we had access to an infinite amount of data. The expectation is over the infinite set of possible data and labels. There are 2 practical questions that arise from our desire to minimize expected risk, which we address in this video. How should we change our training procedures to generalize well? How do we estimate expected risk from finite data? The aim of training a machine learning predictor is so that we can perform well on unseen test data. Is the predictor generalizes well. We simulate this unseen data by holding out a portion of the whole data set. This holdout set is referred to as the test set. Given a sufficiently rich class of functions for the predictor F, we can essentially memorize the training data and obtain zero empirical risk. While it's great to minimize the loss, and therefore the risk on the training data, we wouldn't expect this predictor to generalize well to unseen data. In practice, we have only a finite set of data, and hence we split our data into 2 sets, a training set and a test set. The training set is used to fit the model, and the test set, not seen by the machine learning algorithm during training, is used to evaluate generalization performance. It's important for the user not to cycle back to a new round of training after having observed the test set. It turns out that empirical risk minimization can lead to overfitting. For example, the predictor fits too closely to the training data and does not generalize well to new data. This general phenomenon, having a very small average loss in the training set, but having a large average loss on the test set, tends to occur when we have little data in a complex hypothesis class. Particular predictor F with fixed parameters, the phenomenon of overfitting occurs when the risk estimate from the training data, FEMP, underestimates the expected risk, R true. We estimate the expected risk, R true, using the empirical risk on the test set, R EMP of F, X test, and Y test. If the test risk is much larger than the training risk, R EMP of F, X train, and Y train, this is an indication of overfitting. Therefore, we need to somehow bias the search for the minimizer of the empirical risk by introducing a penalty term, which makes it harder for the optimizer to return an overly flexible predictor. In machine learning, the penalty term is referred to as regularization. Regularization is a way to compromise between accurate solution of empirical risk minimization and the size or complexity of the solution. The simplest regularization strategy is to replace the least squares problem, previous example, with the regularized problem by adding a penalty term involving only theta. So our problem becomes minimizing 1 over n, the norm of y minus x theta squared, plus lambda, norm of theta squared. The additional term, norm of theta squared, is called the regularizer, and the parameter lambda is the regularization parameter. The regularization parameter trades off minimizing the loss in the training set and the magnitude of the parameters theta. It often happens that the magnitude of the parameter values become relatively large if we run into the problem of overfitting. The regularization term is sometimes called the penalty term, which biases the vector theta to be closer to the origin. One practical issue with the training set test set approach is that the amount of data is limited. Ideally, we would like to train our model with as much data as possible. This would require us to keep our validation set small, which would then lead to a noisy estimate with high variance of predictive performance. Now, these two contrary objectives, having a large training set and having a large validation set, can be solved by using cross-validation. K-fold cross-validation effectively partitions the data into K chunks, K-1 of which are used for the training set R, and the last chunk serves as a validation set V. So our entire data is the union of R and V, but R and V are mutually exclusive, and so their intersection is empty. Cross-validation iterates through, ideally, all combinations of assignments of chunks to R and V. This procedure is repeated for all K choices of the validation set, and the performance of the model from the K runs is averaged. After training, we assess the performance of the predictor F on the validation set V by computing the root mean squared error, for example, of the trained model on the validation set. More precisely, for each partition K of training data, RK produces a predictor FK, which is then applied to the validation set VK to compute the empirical risk R of FK and VK. Cycle through all possible partitionings of validation and training sets and compute the average generalization error of the predictor. Cross-validation approximates the expected generalization error, EV of R of F and V, which is approximately 1 over k times the sum of r of fk and vk, where r of fk and vk is the risk on the validation set vk from the predictor fk. The approximation is an approximation because of two facts. First, due to the finite training set. Due to the finite training set, we don't get the best possible value for fk. The second source is due to the finite validation set. And this, having a finite validation set, will give us an inaccurate estimation of the risk, r, fk, and vk. So in this section, we saw that empirical risk minimization is based on the ideas of the hyperclass of functions, the loss function, and regularization. In our next video, we'll see the effect of using a probability distribution to replace the idea of loss functions and regularization.